Zoom. Okay. Okay, can you show us the computer? Okay. Okay, let's see if I do full screen, should come. It's very small, right? So I cannot do full screen. I want to get rid of this view, single page. Continuous scroll is what? Actual size. Well, I think this is there in your proceeding, so you can see I can see from here as well. So we just don't look at the monitors. So the first problem. All right. First of all, the last class I allowed you to submit today because it was the first day. But from today on, you have to submit today, okay? Because you have 1.5 hour time to do it. So at the end of the class, please submit your assignment, homework, so we can start grading it today. Because otherwise, there will be a lag of 1 day, and at the end, we'll have difficulty, right? So try to submit it the same day. If everybody cannot do it, and we need more time, then I will allow you to do it the next day. But try to do it today. So do it fair so that you submit it today. Okay, the first problem is a 2-variable problem, okay? And I give you the hint here. You already seen the optimality conditions for a 2-variable problem. What is that we have to do? We have to compute the first derivative vector, so del f equal to 0, and then we have to check the positive definiteness of the matrix. So form these vectors and matrices. First you solve del f equal to 0. So there will be 2 equations, one for x1 equation, another for x2. You will come and you solve it, and then find the x1, x2 values. If there are multiple solutions, consider each of them separately for del 2f matrix computation, and compute the eigenvalues of the matrix and tell if the point is minimum or maximum. Okay, so everything is written here. So why don't you start working? And if you have any difficulty, just raise your hand or get my attention so we can discuss. Everybody knows how to compute the gradient of a polynomial function, partial derivatives of this function with respect to x1, x2. Okay. Anybody has any issues or problems, just raise your hand and ask me. Okay. Okay, just to start, let's see what will be del f del x1? Somebody computed del f del x1?
3x1 square minus 6x2
minus 2. That's correct. Everybody has got that? Okay. Then move to compute del f del x2.
minus 6x1 plus 2x2 plus 3.
Okay. So both these individually will be equal to 0. So you have 2 equations with x1, x2. Now can you solve it to find x1 and x2? So you can get x2 from one equation as a function of x1 and submit it in the other equation. Yeah, submit it to substitute it in the other equation. Okay, you get an equation like this, quadratic equation. Now you have to solve it, right? You know the formula how to solve it. Let's simplify it a little bit. We can divide by 2. Zero. And if you have an equation which is ax square plus bx plus c equal to 0, then there are two roots x1 and 2 is minus b plus minus b square minus 4ac over 2a. So apply that here and you will get two values of x1. You need a calculator, I think. So what are the two values? 0.481. Okay. So these are x1 values. So what are corresponding x2? 418. Okay. 426. 246. Okay. 246. So, well, this is the procedure that you have to follow. So now there are two solutions, two candidate solutions. Solution number A, or A, we can say 5.58, comma 15.24, right? And B, 0.418, comma minus 0.246. Now at these 2 points, you have to compute the second derivative matrix, okay, and check which matrix is positive definite. The one that's positive definite, the corresponding point is a minima, and the other one you have to do with the minus sign, the second derivative, and then check for the positive definiteness. First one, point A is positive definite. Someone said first one is coming positive definite. Is that right? First one? Okay. We want some verification from some other student. So form the matrix. You know how to form the matrix? So now the Hessian matrix Hx is d2f del x2, d2f del x2 del x1, d2f. It's the same thing actually, del x1 del x2. You have the same value, so you can compute just any one of them. This. Okay, so we already have the derivative computed before. Del f del x1, you differentiate that with respect to with respect to x1 one more time. So we'll get 6x1, and this will be minus 6, and this will be 2. Okay, so that's the Hessian matrix. Now at A, what is the value? A, the x1 is 5.58, so 6 times 5.58 minus 6, because others are all constant, and HB will be 6 times 15.24 minus 6, 2. Okay, can you find the eigenvalues of each of these? So you take the determinant, I don't know how much is that, but 6 times 5.58 minus lambda minus 6, 2 minus lambda minus 6. Determinant should be 0. So now compute the determinant. This times this minus this times this. You will have again a quadratic equation, and then solve that to find it. You can also do the cofactor way. That may be easier here. So the cofactor is, the first cofactor is this quantity only, and the second cofactor is the determinant of that. So this is already positive. Check the determinant. If that is positive, then both cofactors are positive, then that's a minima.
One eigenvalue turns out to be positive and another one negative.
No, then it is not. Both have to be positive. Yeah. So the first one is not, both eigenvalues are not positive. Okay, so it cannot be minima. Okay, if it cannot be minima, then you have to check whether it's a maxima. So how do you do that? How do you determine if it's a maxima? Every element of HA has to be multiplied by -1 and recompute the eigenvalue. Okay? And then if that is also not negative definite, that means it's neither a minima nor a maxima. Then you have to do further test, but in multivariable I have not told you how to do the further test. So you just say that this point is neither a minima nor a maxima. Then move to the next one, point B, and determine if that's a minima or maxima. Yes. 3, 4. Is it 3, 4? Because there is a 6 times x1. The general expression. Oh, sorry. x1 is 0.418. Is it? Oh, yes. I'm doing a mistake. 0.418 here. You're right. I'm trying to plot this function and see how it looks like. Okay, this is how the function looks. Okay, looks like this one is going all the way to minus infinity, and this one is going all the way to plus infinity, and there's something going on here. So what are the points we found? X is 5.5.58 somewhere here, and 15.24. So that's down over there. So I need to extend it. So we'll put some limits now. Okay, let's say I'm going to put limit this way. X range goes between 0 to 6, maybe 7. And y going to 15. Yeah, you see now there is a minima here. You see the function here? There is a minima. The contour says there is a minima here. So this 5.58 and 15.24, it should be a minima. Okay, and the second point, 0.418, right over there, and minus 0.246, somewhere here, there is nothing going on. But to see it better, I need to maybe go a little further on 4 here, go for y range, and x happens to be 0.418. So let me go x range minus 2. It should show up. Okay, that looks like a saddle point to me. So when you have like this is going up, it's a saddle point. So that one, the second point, you will not see any yeah. So this way you can see this a little bit. This way there is a maxima here at this point, and this way there is a minima here. So one side there is a minima, the other side there is a maxima. When that happens, that's a saddle point. So looks to me by graphical means that the second point is not a minima, but the first point should be. Okay. So see if you are getting that. Some of you here told me that you are not getting the positive definiteness. Please check your calculation. Positive? Okay. Then that confirms. And you can see in the graph how the minima comes, right? For which one? A or B? For B, yeah. B is not a minima, not a maxima. So if you don't find both of them maximum for A, no. Both has to be positive. Just check your calculation.
For B, we are getting both types of eigenvalues. So should we check?
Now you have to check the maximization minus. Yeah. But doesn't look like that will also work. But you still have to check. Everyone getting the first one as a minima? Okay, so just look at this surface that I plotted. This is this function. This is x-axis. This is y-axis, right? So if you look at this side, which is your point A, your contour lines are getting kind of enclosed, and eventually somewhere here there will be minima. And you look at this function, right? There is a minima right there. Okay, but this point, the other point, point B is right here, 0.418 and minus 0.246. If I show you this side, what's happening, you see there is a maxima kind of thing, right? Locally there is a maxima here, but I'll show you now the opposite direction this way. You see there is a minima like this. So one side there is a maxima, the other side there is a minima. That's neither a maximum nor a minimum, but the gradient there is 0. The gradient is 0, but that's neither a minima nor a maxima. So those are called saddle point or inflection point. But here is one. From either way, any side you look at it, there is a minima. Either way you look at it locally at this particular point, right here. If you look at this, so if you look at the surface over here, what's happening? If I rotate in any direction, you will see that there is a minima kind of there. So every way you look at it, there is a minima. It's shallow, but there is a minima. Okay. And for the maxima, it has to be the same. Either way you look at it, either direction, any direction you look at it, it should have a hump. Okay, so two-dimensional problems like this, when you plot, you get the idea, then you go and do the math with the theory that we talked about. You can verify and understand the properties of minimum, maximum, and saddle points. Okay.
Ideally, if only the second term is negative in a quadratic equation of 2, like r of 2,
Mm-hmm.
it has both of the roots as positive, like a square minus 2ab plus b square.
Right.
So you could directly say that both of the
Yeah.
if only the second term is negative.
It depends on the a and b as well, the other terms, because you have to do the eigenvalues before you can figure it out. You have to compute. Eigenvalues, the value doesn't matter. The sign is important. Are they positive, or are they both positive, or are they both negative?
There was this like term minus b upon a. If that is positive, if that is negative, then that you have both of the roots are positive.
Why?
Roots
Because
of a quadratic equation could be figured out by looking at the equation instead of pointing.
you can figure it out. If you can figure it out, if it's a quadratic equation, you can figure it out. Yeah, you could do that way also. Okay, shall we move to the next problem? Has everybody done it? All right, so let's move to the next problem. This one is to be solved using golden section search. It's a single variable problem, x cubed minus 3x plus 2. You have to minimize within the range x going from 0 to 2. So here bounding phase is already done, and you have been given that the minima is bracketed between 0 and 2. Okay. Now we'll not do all the way to find the minima. We'll just do 3 iterations of golden sections to see where you are going, and then you also find the theoretical optima. So I would solve the problem, the b first. Let's solve b first, 2b first before you go to a. So can you find the minima theoretically of this function? How will you do? It's a single variable function.
First of all, derivative first order
Equal to 0, and find the roots, and then second derivative should be positive. Yeah, check that. So what is the root you are getting? Plus minus 1. Okay. Then calculate the second derivative. At both places you have to do, right? So here's what's happening with this function. Minus 1 and plus 1. What's happening in minus 1? Maxima, and plus 1 is a minima. See if you are getting that. Okay. So now So what is the theoretical minima then? Theoretically finding the minima is x equal to 1. Okay, so that solves the problem B. Now move to problem A, where we have to confine ourselves between 0 and 2 and use an algorithm, golden section search, to locate this point 1. But you need lots of iterations of that, so we are not going to do that. We are going to do only 3 iterations. So our search is included between 0 to 2, right? So first thing you do in golden section is normalize so that the range goes between 0 to 1. And I suggested in the problem it says how to do that. So get x converted to y with that transformation and write f as a function of y. Can you do that? So y I have already computed here, y equal to x by 2, right? Okay, now substitute x equal to 2y in the fx term, okay, and you get the function as a function of y. So keep that function ready, okay, and now what are the 2 points you have to take? Now your y bound is 0 to 1, right? So 2 points you have to take inside and compare. What are those 2 points for y? Yeah. So 0.618 and 0.382. So compute f at y equal to 0.618 and f at y equal to 0.382. You may need your calculator for that. Or you can create an Excel sheet and just keep doing it in the Excel sheet if you have a computer with you. Okay, which one is coming to be higher? Is 0.382 or 0.618? 0.618 has a higher value? They look almost the same here to me. 0.382. Oh, okay, that's why I can't see it. Okay, so but 0.618 is bigger, huh? Okay, so which part will you eliminate then? 0.618 to 1. Okay, so you see when you eliminate 0.618 to 1 here in this picture, I'm not eliminating 1, right? My optimum point, which is at 0.5 here. Okay, so that's one iteration. Now move to the next iteration. So you're left with 0 to 0.618. Now you will go from either end 61.8%. One of them you will see magically will be the same as 0.382. And the other one will be new. So you just have to compute at one new point the function value. It's better if you make a sketch like this. So draw a 0 to 1 line. So let me show you here what you should do. So here is my 0 to 1. I've got 2 points, 0.382, 0.618. So what we have seen is we can eliminate this part because this is higher, slightly higher than that. Now I am left with this part. So now 1 point will automatically come. The other point will be here. So find out what is that point. Now these points are going to be 61.8% of the whole range. So this whole range is 61 is 0.618. So 61.8% of 0.618 is how much? It's 0.382. Yeah. So one you get 0.382, other will be 0.382 from 0.618. So subtract 0.382 from 0.618 and you will get the new point, 0.236. At this point compute the function. So and the other one is matching with that, so you don't have to compute the function value. Only one point you have to compute and compare. Is that clear? And then apply it one more time. So now there will be reduction. Figure out which part will drop off, and then the remaining part you go again 61.8% from either end. So people at the back, are you okay? Are you with me? Or if you're lost, just raise your hand. Okay?
So once Y1 value is higher at 0.618, what is the next step?
So you've got 2 points now in the second iteration. Have you compared? So, huh? So 0.236 is higher? First step, yeah, 0.618 is higher. So which part will you eliminate? From 0.618 to 1 you will eliminate, right? So you will be left with 0 to 0.618. Now we go to the next iteration. Of this range 0 to 0.618, you go 61.8% from either end. And you will have two points. You will see 1 point is exactly same as 0.382, which you have already evaluated. 1 will be new. So evaluate that new function. And now compare these two, again eliminate some part based on the comparison. So like that you do one more iteration. Is that clear to everybody? Not clear to you? Speak up.
How we can find the next point?
So have you done the first part? All of you done the first part? And figured out this part will be eliminated? Okay. So now we are left with this, right? So what's the algorithm? The algorithm says whatever part remains, we will go 61.8% of that from either end. So find those 2 points in the second iteration. Find them. And you will see that one of them is going to be matching 0.382 and the other one will be new. So compute that function value and again compare with 0.382, function value at 0.382, and eliminate a part. So like that you proceed one more time. Okay? So the confusion may be how to get this point, right? So now you have left with 0.618 and you go 61.8% of that. So how much is this? This is 0.382, right? This you have to get from either end. So 0 plus 0.382 will be 0.382 and the other end will be 0.618, which is the other end, minus 0.382. From this end I will go 0.382. So this you compute and you will probably see this as 0.2 something, 6 and 3. So this is 1 point, 0.236, and this is another point, 0.382. Now compute the function values at these 2 points and see which one is bigger. 0.236 is bigger. So what you have to eliminate? 0 to point. So this gets eliminated now. So now we are left with this small region here. And then do one more time. 0.618 of that much region from either end. You should get a feel of this, how this is working. Just 3 iterations. So 3 iterations, as I said, is not going to give you the minimum, but you make sure that its minimum is inside your range always. You have not eliminated the minima.
Sir, for the third iteration, the
Yeah.
range is 0.236 to 0.382.
No, 0.236 to 0.618 before the third iteration, right? You eliminated 0 to 0.236, right? So what is the range? Range is 0.618 minus 0.236, which is 0.382. So now 61.8% of 0.382, that much region you will go from either end of this range. And again you will see one of them is going to be common, and that is 0.382. That will stay. Is that clear? Okay, third range, what is the third range? So third range, here we have 0.236, here we have 0.618. So what is the difference? 0.382, right? Okay. Now 61.8% of 0.382, how much is that? Can somebody tell me? 0.618 times 0.382. 0.236. So you will go 0.236 from either end. So add 0.236 to 0.236 to go from here to get the point, and subtract 0.236 from 0.618 to get to the other point. You will see that this point is okay, I don't know now. This one seems to be 0.382. And how much is that? This will be 0.618 minus 0.236. How much is that? So 2, 8. Oh no. Oh, 0.382 is that one. Oh, okay. So you have to add now 0.236 to 0.236. How much is that? So 0.382, and this is 0.472. Is that clear? So you find out how much to go from either end. From the lower bound you add that, the upper bound you subtract that amount from the upper bound, and then you get the 2 points. Now compute the function values at these 2 points and see which one is which region will be eliminated. Don't do it mechanically. Try to understand what's going on, because yeah, go ahead. Right. So you eliminate from 0.682 to 1. Yeah. Right. 0 to 0.618. That much is remaining. Yes. Now 61.8% of that you have to go from either end to get the 2 new points, 2 points. Yeah. Yeah. Every iteration you will have 2 things to compare, and based on whichever is higher you eliminate. No, where is the derivative here? There is no derivative here. No, we are using the algorithm now. There is an algorithm, the golden section doesn't have any derivative. Derivative was for part B, to find out the optimum exactly. We already found that. It's +1, right? Now we are trying to use a numerical algorithm, which is the golden section search, to see if we can find that minima. All right? So that doesn't use any derivative. So we are only using function value comparison. 2 points we are comparing. Based on whichever is bigger, we are eliminating some part. So you keep on doing this. Yeah. In the second iteration, again, there are 2 points. Yeah. Yeah. Right. Yeah. So let's concentrate on the first iteration. Okay, please don't talk. So the confusion is that how to proceed, right, with these 2 points. So the part B that I talked about, the B that you've done, is completely with theory. Okay, there is no algorithm there. Once the problem is, as I told you, once the problem is given to you, there exists a minima, and you can use this theory like derivatives to compute what is the actual optimum. We have done that in part B, and in this problem we have seen x equal to 1 is that optimal solution. Now in part A, we are trying to find the same optimum, not using theory but using a numerical algorithm. That is the golden section search, right? And it works in iterative manner. In one iteration we are not going to get the minima, right? And we are not using any derivative in the golden section search. So what is the search? Once you have bracketed the bound, the optima between lower bound and upper bound, in this case I told you the optima lies between 0 and 2. I told you that. If I didn't tell you, you would have used the bounding phase to find it. Let's say you found 0 to 2. Within 0 to 2 the optima lies. Now I need 2 points inside 0 to 2 in order to proceed with the algorithm. First thing we did is we normalized so that you can use the golden number actually. So we did x to y conversion, everything now between 0 to 1, and I have a function value defined in y. First iterations, you always have these 2 points, 0.382 and 0.618. Okay. So you compute the function values at these 2 points. In this case 0.618 has a higher value. So we eliminate 0.3618 to 1, that region, and we are left with 0 to 0.618. So we are saying our optima lies between 0 to 0.618. Remember from the theory the optima lies at 0.5 in terms of y, right? So it's included in our range 0 to 0.618. Now we move to the second iteration. Our range is now 0 to 0.618. So the algorithm says again go 61.8% of this range from either end, and those are your 2 points to compare. So compute what are these 2 points. Can you do that? 61.8% of 0.618 from either end. So that becomes 0.382 from either end. So the lower bound you add 0.382, upper bound you subtract 0.382. So then you get the 2 point. At this 2 point you compute again the function values and decide which part should stay and which part will be eliminated. And check immediately if 0.5 is included in your range. If not, you have done a mistake. Your 0.5 should be always included because that's the minimum, right? And then repeat one more time this whole process, and that's the end of, because I asked you to do only 3 iterations. 0.382 to 0.618. I can check right here in my plot. One second. Yeah, sorry. So 0.382 to no. Oh yeah, 0.382 to 0.618. Yeah, seems to be. Yep. You see 0.382 is somewhere here, 0.618 here, and the optima is included. Yeah. Is that what everybody's getting? Okay, you can also verify how much would be the range after 3 iterations. I gave you a formula. What was that? The formula was 0.618 to the power n minus 1 times b minus a. That will be the final range, right? So n is the number of function evaluations, but I asked you to do 3 iterations. N minus 1 is also iteration. So if this is iteration counter t, so we did 3 iterations. So b is 1 in terms of y and a is 0. So 0.618 to the power 3 times 1. How much is that? Compute that through your calculator. So your range is after 3 iterations should be 0.236, is it? When you have 0.618, 0.382 to 0.618, takes the difference, it will be 0.236. So there, 4 function evaluations you have done, but 3 iterations. Because first iteration needs 2 function evaluations. After that 1, because 1 is already coming from before, right? So this n minus 1 actually in this formula is the number of iterations, because n is the number of function evaluations and n minus 1 is the number of iterations. Okay? B is the upper bound, A is the lower bound. So in this case it's 0 and 1. That will be the range. The range that you get, the range that you end up with after t iterations is this quantity. So this is actually range after t iteration is this, right? And that's a check. You can have a check to see if everything is all right. Everybody is done at the back? both problems? Okay, let's move to the third one. This one requires steepest descent method. Okay, now it's a two variable problem. It's a two variable problem given, we have to minimize it, estimate the minimum of the function. So here I'm not asking you to again find the optimal point by theory, but just use the steepest descent. But I will plot it in a minute and show you where the optima is. But so the starting point is 0, 0. And okay, no, it says use optimality conditions to solve the line search. What is it, a line search? Two iterations, steepest. No, it's not a line search. Oh, sorry. No. I misunderstood here. So the last line says, okay, so once you have the steepest descent, what are you doing in the steepest descent? You will find the negative of the gradient at the current point, which is 0, 0 to start with. So you will get the negative of the gradient direction. Now you have to do a line search. Line search means you have to find the optima along that line. Right? So there is a line specified now, which is the negative of the gradient starting from 0, 0. Now it's a single variable problem, as I said, right? So you could use actually golden section search to find that. But as you have seen, you need probably 15 iterations of golden section to get really with the precision. To avoid that, we are going to use optimality conditions. That means the first order conditions and the second order conditions to locate the minima along the line. Okay? So let's go step by step. So first, you should find the gradient at the point 0, 0. So I would say first do it this way. Iteration 1. That's your first iteration you're doing. Say iteration 1. Okay? First thing you should do is compute S0. Your t is equal to 0. S0 is minus del f x0. So now you need to write a general expression for del f x. Write that. This is del f del x1 and del f del x2. Can you write this? What are these two expressions from the equation given? Write them first. Okay. Looks to me at 0 and 5 or close to 5. 9? Huh? Okay, derivative. Okay, you are computing derivative at 0, 0. Okay, what is that? 0 and 9. Okay, so if this is, so evaluated at x0. Yeah. So this is 0 with the minus sign, the negative of the gradient, or? Yeah. So we can check in this plot here. You see, you are at 0, 0, which is here, right? This is x equal to 0 and y equal to 0, you are here. and the contour line seems to be telling me, yeah, gradient, negative of the gradient, because here is the minima. So negative of the gradient should be in that direction, which is 0 and 9 or 0 or 1, it doesn't matter. By the way, 0 and 9 is the same direction as 0 as 1, right? All it says is the direction. It's just that this is a little larger magnitude, but it's the same direction. So it's telling you that x-axis you don't move, y-axis you move. That's what it says. So x-axis is, in my plot here, x-axis is this axis, y-axis is that. So it says from this point you should move along y to get to the minima. Okay, so everything is working so far. So now let's apply. So now that you found it, how will you do the line search? Yeah, write down x alpha. So let's do with 0, 9 as you've got. So what is x alpha? Will be x naught plus alpha times s naught. Okay, so x naught is 0, 0. Alpha times s naught is 0, 9. Okay, so what is that? That is 0 and 9 alpha. Okay, so now go and substitute it in f. x1 equal to 0, x2 is 9 alpha. So you write capital F as a function of alpha by writing this way, 0 and 9 alpha. Can you write that? So substitute for x1 equal to 0 and x2 9 alpha. So what you get is 2 minus 9 alpha plus 9 alpha minus 4 square. Okay, now I've got a single variable function. I'm not going to use golden section to do it. I'm going to use the optimality condition. So how do you find the optimum of such a function? First derivative equal to 0, second derivative should be positive. So try that and find alpha star. Half? Okay, good. So then what is x1? That's your new current point, x1. What is that? So you have to substitute at it 0 and 9 alpha, right? That was a general expression for x alpha. So it will be 0 and 4.5, right? 9 times half. Is that clear? Okay. And that seems to be the point here. 4.5 is somewhere here. So that seems to be okay. So we see that this is already an optima, but the algorithm doesn't know it. So we'll continue with it. So this is my x1. This is the end of one iteration. Now we'll do the second iteration. So say iteration 2. By the way, I told you that this line search is going to terminate at a point where the derivative is orthogonal to the original search direction. So let's compute the derivative at this point, fx1, which we need here as well. So s1, what will be s1? Will be minus del f x1. Compute the derivative at this new point. Both 0, 0? What does it tell you? If the derivative at the point is 0, 0, what does it tell you? This is a candidate for minimum or maximum, right? So then you have to do, because we are minimizing here, so it is likely to be minimum. Excuse me. Now I want to check whether this direction is orthogonal to the previous one. When it is 0, 0, it has to be orthogonal, right? So no matter what is it was. So but then if you do S0 dot product with S1, it is 0. So that usually happens. Okay, so when I have a 0, 0, then there is no point for me to continue any further. So then you said this point that the optimum is 0 and 4.5. So you don't have to move any further. But if this was non-zero, then you had to move. Actually, there was a typing error. I realized there should have been a square here. The first part of the function should have been a square here. So I missed that part in the typing. The problem became easy. But anyway, you can try at home doing it the square.
So steepest descent will converging at most 2 iterations for quadratic case. Is it right?
Yeah, quadratic it should, as I said. So if I don't have the square there, it's a quadratic function, right? And in 2 iterations it converges. But if there was a square there I put, it may not converge in 2 iterations. Is that clear? Everybody's done it? Okay. Yeah. Second iteration, how it becomes 0? Have you computed the gradient at the new point? Del f at x1. What is del f at x1? Have you computed that? How will you do? So you have to write the general expression here, right? General expression for the gradient. 2x1 and then here minus 1 plus 2 x2 minus 4. Okay, now substitute x minus. Yeah, so 2 times x2 minus 4. So this will be 2 x2 minus 8 minus 9. Yes. So now you substitute x1 equal to 0 and x2 equal to 4.5 in this. So what do you get? Because at this point you have to compute the gradient. Right? It will become 0 and 0. Okay? Any other question? You understood then how the steepest descent work? Line search work? How the line search work? Okay, we'll come back to this if you have time. Maybe we could do it the square again, or you can do it at home. Okay? Put the second term square and then redo the problem. Then you see you need 2 or 3 iterations. That's why I said 2 iterations, because it might need more than 2 iterations. Okay, so let's move to the 4th problem. Yes, to get the new gradient. Yeah. See, every new point there will be a new gradient. So you best to compute the gradient function as a general function of x and y, or x1, x2.